Archimedes. Hi, Stuart. Okay. Today is new. Today is not difficult to master, boys and girls. Today is not difficult to master, but it is difficult to understand right away. So as opposed to trying to get this all in on Monday, what I'd like to do is I'd like to give you 15 minutes worth today, and then Monday we'll get to it. But you'll have a decent amount of time to work today and answer or ask some questions. But on Monday we need to make some progress on this. So today we want to cover something called implicit differentiation. I don't know how good I am at teaching this because I've only done it, a couple times, and so I'm going to do my best to explain it here, and bear with me if I make a mistake. But there are what we call explicit equations and implicit equations. Let me give you an example of some explicit equations. Y equals 2x minus 5. Y equals the sine of 3x squared. Y equals 8 over x minus 2. Can somebody maybe identify what makes something explicit? It's y equals, right? So in other words, it's solved for y. Most of the times, these represent functions. And that's why we like to work with them. We like functions. And today, we've been working with so far we've worked with all sorts of different derivatives, but they've all been derivatives of functions. You can find the derivatives of things that aren't functions. For example, let's say this, x squared plus y squared is equal to 9. Does anybody know what that graph looks like? That's a circle. It's a circle with a radius of 3. And so that is not a function, but yet we can find the derivative of it. This is an implicit equation. Here's an example of another implicit. X divided by y equals 9. Here's an example of another one. Nine xy plus y is equal to x. Right. Right. Sean brings up a very good point. He says, let's say we wanted to differentiate something like x squared plus y squared equals 9. We could solve for both parts of it, the semicircle on top and the semicircle on bottom. And we'll look at an example like that on Monday. But when you see me take the derivative of this using implicit differentiation, it's infinitely times easier compared to solving for y. So there's times where we like implicit differentiation. There's times where we have to use implicit differentiation. We don't really have any other choice. So let me just back up here and address some terminology issues. F prime of x specifically means the derivative of a function with respect to the variable x. I'll let you write that down. And when I teach you guys the skill today, the process, you're not going to have any issue with it. But to help you understand what's come up so far, it's like we start with this. We start with f of x, and we get f prime of x. How does that happen? How do you just get to make a prime spot there? Well, we learned we use the formal definition. We learned all the shortcut rules. But what allows us to do that? We've also used this terminology, which basically says the same thing, except what part of the definition might be left out here when we look at that? Function. We don't know if it's a function. So this simply says the derivative with respect to x. That's all that says. That doesn't say it's a function. Well, this doesn't say it's a function either. but it does identify what we're taking the derivative of. We're taking the derivative of y. With respect to x. When we find the derivative of a function, we change x a lot, but we're actually finding the derivative of the function. So here's some terminology. Let me show you how this works out here, okay? Find the derivative of the circle x squared plus y squared equals 36 using implicit differentiation. This is where I'm going to try to make a connection I haven't tried before. We'll see how it works, okay? Just trust the process so you understand it, and then I'll show you the shorter way of doing it. If we want to find the derivative of that, we would take the derivative of each piece, namely the derivative of, with respect to x, of x squared, plus the derivative with respect to, we're still going to take the derivative with respect to x. It's out. We're always going to work with x. We like to solve for y, but we haven't solved for y. So we're continually using derivative with respect to x. Okay? Of y squared equals the derivative with respect to x of 36. Well, I know that looks somewhat silly, but it's really not too bad, okay? Well, let me show you what happens here, okay? If I go like this, what is the derivative of x squared? 2x. What's the derivative of 36? But there's something that happens here, okay? There's something interesting that happens right here that I need to work out. This is problematic because I'm taking the derivative and I have this variable here, but I have nothing that represents y, okay? So I'm going to show something that looks like it's cheating, but it's really not. D over dx of y squared. And then watch this. D over dy. Now, I added a y in the denominator, so I should also add a y to the numerator. I can't just add that without adding a y to the numerator. I add it there. Well, I can find the derivative with respect to y. What is this thing? 2y. So I have 2x is equal to, well, I'm sorry, 2x plus dy over dx times 2y is equal to 0. So all I did was I basically took the derivative of that y squared like you would think you would, and I attached a dy over dx onto it. This represents the derivative of y with respect to the variable x. If I want to solve for this piece, how would I do that? What would I move first? I'm going to subtract my 2x over. So I get dy over dx times 2y equals negative 2x. Now what do I do to both sides to solve for this? Divide my 2y off, and I get the dy over dx is equal to negative x over y. Now, it looks confusing the first time you see it through. The very important point lies right here. I want you guys to see how we were able to kind of cheat by adding a y up top. It tells us the derivative of the function y, or not the function, the derivative of the equation y with respect to the variable x is that. And that does give us the rate of change. So if you knew a point on this, okay, all you would have to do to be able to identify the rate of change would be take that point, that xy, and plug it in for x and y. We're used to always plugging in just things for x, right? Well, now you can plug it in for x and y. Question? Right here? I needed to divide the 2y off so I could just solve for dy over dx. dy over dx represents the derivative of y with respect to x. So I want to solve for just that piece to identify what it actually is. Now, furthermore, I will tell you guys this. Write this down because you're going to love this question. Yes, in fact, you're going to write it like this. Notation for dy over dx, instead of writing it like this, most people choose to write it like that. And that is the way that we will choose to write it. You like that better, don't you? So there's really four basic steps that you'll use for implicit differentiation. I just have four basic examples on the back side. They're going to go really quick. The first thing that you do is you derive each term. Separately. Second step, make sure that you add a y prime every time you derive a term with y. Third, let's gather. Gather all y primes on one side. Divide and solve for y prime. You'll see the process laid forward. It's something that you guys will pick up very well. I just want you to know that the first time I saw implicit differentiation, I didn't understand it. I didn't understand why you could just replace it with a y prime. The magic happens here. When you have a dy over dy, which is 1, but you replace the y over there, and you get this. You get the derivative of y with respect to x, and you're allowed to take the derivative with respect to y of y squared. That's where the magic happens. And so therefore, we're able to do this somewhat unorthodox method. Yeah. Kind of. Yeah. Yep. Yep. Yeah. Let me show you how easy it is. Use implicit differentiation, find the derivatives of the following equations. You can see if these get more complex, it would be tough to solve for y in some of them. The first one wouldn't necessarily be that bad, but as opposed to solving for y, let's just take the derivative. So we're going to find the derivative of y with respect to x. What do you do? What do you get when you take the derivative of this? 6x minus, what's the derivative of 4y? 4, and every time you take the derivative of something with y, you have to attach a y prime equals, what's the derivative of 4x? 4. Now it's algebra. Gather all the terms that just have a y prime on one side, divide and solve. So if I subtract my 6x, I get negative 4y prime equals 4 minus 6x. Now do what? Divide by negative 4. Y prime is equal to 4 minus 6x divided by negative 4. That's it. You could say negative 1 plus 3 halves x if you want. This one's a little bit different. B is a little bit different. What's the derivative of y to the third? 3y squared y prime minus 5 minus, oh, I'm sorry, mine didn't pick it up. It's a plus, plus 2y prime equals 3. Well, now I got 2y primes in that scenario. Well, it's no big deal. I just follow my method. I get everything on one side that does not have a y prime. So I'll add my 5 over. I get 3y squared y prime plus 2y prime equals 3 plus 5. What can I factor out? A y prime. And you're left with 3y squared plus 2 equals 3 plus 5. Oh, which is... Sorry. I was thinking so far ahead to the problem, making sure I didn't make a mistake that I did that. How do you solve for y prime? Divide by 3y squared plus 2. Divide by 3y squared plus 2. So y prime is 8 over 3y squared plus 2. The x's entirely went away in that situation. Any questions on either of those two? Okay, let's try 2 more, and then you guys can get to work here. X plus 2y squared equals 3x to the third plus 4y to the fourth. What's the derivative of x? 1, 2y squared, 4y y prime equals 9x squared. What should you do now? Yep, get everything with y prime on one side, so 4y times y prime minus 16 y to the third times y prime equals 9x squared minus 1. Now, you guys are absolutely right that the greatest common factor is actually 4y y prime, but I don't take out the greatest common factor. I only take out the, because that's what I'm trying to solve for. So good thoughts to do that. In this case, not necessary. Divide by the 4y minus the 16y to the third. And you get y prime is equal to 9x squared minus 1 over 4y minus 16 y to the third. Now, again, I'll go back to Sean's comment earlier, which was good. He said, you know, we could solve for y and then take the derivative. Well, as you can see in this case, it would be pretty difficult to solve for y. But yet we found the derivative pretty easily. Last one. You sure? Last one. I do have a problem. I have xy. Anybody want to guess what that means? It means the product rule. Okay? So let's do this part first. Let's start back here. What's the derivative of 5y squared? 10y times y prime. Derivative of 9x? 9. And 3xy, I'll need to do the product rule. I'm going to say that 3x is one function and y is another function. So I take the derivative of 3x, which is 3 times y, left alone, plus the derivative of y, which is y prime, 1y prime, times 3x left alone, plus that 9. So there I go. And now it's the same process. We gather terms on one side. So I'll have this 3xy prime I'll subtract my 10y, y prime. And then on the other side, I would have a negative 9 and a minus 3y. Factor out my y prime. 3x minus 10y equals negative 9 minus 3y. Divide. Y prime is negative 9 minus 3y over 3x minus 10y. Done and done. So again, implicit differentiation can be very useful. It's not magic that we end up with a y prime there. It's simply notation. Understand that we're deriving y with respect to x. When you take the derivative of x, you don't have to attach anything. But when you do for y, you have to name it that is a rate of change by adding that y prime. So anyway, that's it. You have time to work. Goodbye, Stuart. We hope you have a good weekend.